Here, this is my physics lab 2. In this lab, we are going to observe the motion of some object that is going to be moving in a parabolic trajectory. We're going to compare this with two predicted positions from a computational model, one that considers drag force while the other doesn't. And our goal is to demonstrate the principles of Newton's second law and the effect of the drag force and gravitational force using computation experimental models. Um, the system is going to be a wadded up piece of paper. The surroundings is everything else. And some aids we're going to use our glow script and the tracker app. So let's go into the basic physics principles. First one is Newton's second law. This was explored in lab 1. The momentum principle for velocity update. And then you have the gravitational force and drag force in this lab, where the gravitational force is the attractive force between the Earth and the object, which we just say is negative mg in the y hat direction. And the drag force is this equation, negative b times magnitude of v squared times v hat, where b is a proportional constant. And terminal velocity is just defined as when the gravitational force balances out the drag force. So procedures for this lab. First, we're going to obtain the observed position, compare that with obtaining a computational position in Excel. So first, we want to film the video. Okay, so there's the motion of the wadded up piece of paper. Upload in the tracker, and as you can see, we want to put our X and Y axis and calibrate the 1 meter. And then we want to track the position frame by frame using the tracker app. So you can see, track the frames of the trajectory, and then upload the data, this data, into Excel. To obtain the initial velocity and position for our computation, I got it from the data from the tracker. So this is my initial position, and then to get initial velocity, in the X direction, I just used the first 2 bullets for the X position. And then for the Y position, I actually got time to the peak, just so I have a more accurate Y velocity component. Okay, so here's my code. As you can see, there's a lot of things that we need to define in the yellow boxes. Ball mass, 0.005 kilograms. Here's the initial position and velocity we just discussed in the previous slide. Time starts at 0 and it moves at 1/30th of a second because of our frame rate. Gravity is 9.8, and since we're not doing drag yet, our b is 0. Time, this is the time it took to film the video, and then here's my forces. Since b is 0, F drag will not be considered, and gravity as here, and then position and velocity update here. So this is what we get when we just take into account gravitational force, which is the orange line, and it predicts a higher trajectory than the one we saw. So what's missing is the drag force. So let's take into account the drag force this time. I set my b equal to 0.005, and that will put this equation to use here, which we discussed already. And here's the final result. The gray line is now the computational model with gravity and drag. Blues are experimental. As you can see, the experimental sort of lies in the middle, but it's kind of off. So there are sources of error. Let's discuss that. Outside forces, there could have been other, like wind in the room coming from an air conditioned vent. The ball shape may not have been perfectly spherical. Um, and then the tracking app could have gotten like the wrong position on the ball at different times and not 100% calibration. So what does this mean? Do any of our models predict terminal velocity? Well, terminal velocity is when the slope of velocity flattens out, because that means zero acceleration. And when there's zero acceleration, that means the forces are equal. And like we said, terminal velocity is when drag equals force of gravity. So there's no flattening out in our first computational model when we just did gravitational force. So no, that does not predict terminal velocity. As you can see, when we take into account drag, the velocity sort of starts getting less steep. So that could suggest terminal velocity. And then how would the time change if the object was thrown straight up? Well, the time would be longer because we now have a time to peak component, meaning it remains in the air longer, and the velocity has to decrease, reach 0, and then start increasing again. And also, we have these equations for like time, and when it's thrown at an angle, you have sine of theta in the equation, and we know it's always going to be less than 1 if the angle is less than 90, meaning the time that's not straight up and down is going to be smaller. Thank you for watching.